Hey everybody, this is example number 1 for mechanics of materials covering strain transformation. The problem statement that we have is the differential element shown in the figure below experiences a state of plane strain. So the strain in the x direction, epsilon x, is equal to 600 times 10 to the negative 6. Epsilon y, the strain in the y direction, is equal to negative 400 times 10 to the negative 6. And then the shear strain, gamma xy, is equal to 300 times 10 to the negative 6. So the other, since this is a state of plane strain, the other three strain components will be 0. So we have these two normal strains, epsilon x and epsilon y, and we have one shear strain. And so we need to find the equivalent strain on this element if it's rotated 30 degrees clockwise from the original position. So on the left here is the original, so on the left here we have the original coordinate system. We have x and y. And in red we have the element, we have the undeformed element, and then the dash green represents the deformed element. And also we show the relationship between the strain and the deformation. And then on the right here we show the original coordinate system and the rotated coordinate system. So our new coordinate system is rotated 30 degrees clockwise. So 30 degrees clockwise. So from x to x prime, it's 30 degrees. So the reason we're showing negative is because when we're doing these calculations, counterclockwise from the original x is counterclockwise is positive. So clockwise will be negative. Also, before we proceed with the solution, going back to the figure on the left, since we have a positive strain in the x direction, this element is deforming, it's getting longer in the x direction. And then we had a negative strain in the y direction. That's why it's getting smaller in the y direction. And then we had a positive shear strain. So this angle here is going to be less than 90 degrees. That means this is positive shear strain. So the first thing we're going to do is calculate the strain in the transformed strain in the x direction, the normal x direction. So here's a formula for calculating strain in the new coordinate system. It's going to be equal to the normal strain, epsilon x plus epsilon y divided by 2 plus epsilon x minus epsilon y divided by 2 times cosine of 2 theta plus the shear strain divided by 2 times sine of 2 theta. So it's simply just plugging in the numbers. So just one thing to note here, just remember that theta is negative because we're measuring, since our coordinate system is going clockwise from the original x-axis. If it was going counterclockwise, then it would be positive. So just make sure this is negative theta here, negative 30 degrees, and then also negative 30 degrees here. So the transformed strain, epsilon x prime, is equal to 220 times 10 to the negative 6. Next, we're going to calculate the strain epsilon y prime, the strain in the y direction in the new coordinate system. And the formula looks very similar to the strain, to the transformed strain in the x direction. The only difference is that instead of having a plus, and we just have a negative sign. In the epsilon x prime, this was positive, and then when calculating this epsilon y prime, this is negative and negative. So if we go back to the formula before, we'll see we have positive here, but now when calculating the strain, the transformed strain in the y direction, we have negative, 2 minus signs. So again, we just plug in the numbers, and noting that theta is negative 30 degrees, we find that epsilon y prime, the strain in the y direction in the transformed coordinate system, is equal to negative 2.01 times 10 to the negative 5. And lastly, we're going to calculate the shear strain in the new coordinate, in the transformed coordinate system. So here's a formula for shear strain. So the shear strain, the transformed shear strain divided by 2 equals negative, and then epsilon x minus epsilon y divided by 2 times sine of 2 theta plus the original shear strain divided by 2 times cosine of 2 theta. And I just simplified it even further. I multiplied the whole equation, the left and right hand side, by 2. And then finally we just plug in the numbers. So the shear strain, the transformed shear strain, is equal to 0.001. And then I also drew a representative model of what it would look like. And so here's the element in the new coordinate system and the corresponding deformation and the corresponding strain and deformation. So this is the end of this example. Please subscribe to the channel, like the Facebook page at facebook.com/engineeringexamples, and also please check out our website at EngineeringExamples.net. Thanks.